One of the present generally noticeable and high-level physicists has communicated his assessment regarding this issue. Michio Kaku, recognized for his extraordinary contributions to the fields of physics, has recently affirmed that the James Webb Space Telescope has found 6 enormous galaxies that researchers thought couldn't exist. These examinations have the potential to open up new aspects in our scientific understanding of the universe. The discovery is both exciting and progressive, testing existing speculations about the evolution and advancement of galaxies. It is, therefore, worth watching out for these developments. The affirmation by such a recognized researcher as Michio Kaku highlights the significance of these discoveries. Michio Kaku is an extraordinary figure in the scientific field, a physicist of American and Japanese heritage. He is viewed as a specialist in both traditional experimental physics and quantum mechanics. Unlike some more moderate and doubtful researchers, Kaku does not belong to that group and has been open to the astounding results of the James Webb Space Telescope mission. His willingness to embrace new revelations and share them with the public highlights his commitment to advancing our understanding of the universe. We are genuinely glad that this recognized researcher has chosen to end his silence and openly share what can no longer be denied. The excitement and nearly entertained tone of the famous theoretical physicist are apparent in his remarks on the discovery made by the James Webb Space Telescope, expressing that this has been a feature that has provoked his curiosity. Join us to explore the implications of Michio Kaku's revelation of these 6 gigantic galaxies. Kaku is a researcher who has consistently been willing to consider new theories throughout his life. He has illustrated a receptiveness to ideas that challenge the norm, grasping that Einstein's conditions of relativity and Newton's laws, while fundamental, are insufficient to capture the full complexity of the universe. Kaku understands that the discoveries of the new telescope have the potential to advance the scientific field, although many of his colleagues have not been able to adopt this view. This is creating concern and insomnia among the Big Bang defenders and rivals of quantum mechanics. However, this only incites laughter from Kaku. The JWST has uncovered the discovery of 6 enormous galaxies dating back to the earliest times of the universe. Each of these cosmic systems contains more stars than our own Milky Way. Notably, they formed only a brief time after the Big Bang. The team of cosmologists who made the discovery has named these remarkable worlds universe breakers, as, if confirmed, they would change our entire understanding of the universe. The implications of these discoveries are significant, suggesting that the universe's early years were far more powerful and complex than previously thought. Something doesn't fit here anymore. The theory of the Big Bang tells us that the universe was a train wreck after the initial event. The first solid objects required countless years to form, and it took numerous additional years for the objects to reach sufficient density and produce light. The development of complex structures, such as galaxies, was expected to happen much later. Some of the newly found galaxies surpassed the Milky Way in size, and their immense luminosity shows that they were likely forming many new stars every year, while our galaxy forms stars only sporadically. It remains uncertain precisely when the first galaxy formed. Scientists have not been able to determine this up until now. The only thing that is clear is that initially, there may have only been single stars or groups of stars that ultimately joined together to form increasingly large gradual additions until dwarf galaxies fostered. The small galaxies experienced interactions with different systems and gradually developed, according to past hypotheses. Extremely organized and large galaxies could not have existed at that time, which raises whether or not the universe is much older than recently accepted or whether complex cosmic arrangements grew significantly sooner. This situation is challenging to accept for moderate science, which still finds issues with this model, and several aspects of physics strongly refuse to acknowledge this discovery. Moreover, they question potential errors in the age estimations. Kaku is aware of this and had this to say: "There are numerous models of old and misleading speculations that tenaciously endure in view of the prominence of certain researchers. Many of these hypotheses were only disparaged when an essential investigation uncovered their deception. Hence, the major work in any science, particularly in physics, rests within the experimentalists who keep the scholars alert and awake. In fact, on Earth, we have barely any familiarity with the valid origins of the universe. This statement from Kaku underlines the importance of constant trial and error and validation in the scientific process. The theory of how things came to be was laid out in 1927 based on observations of the expansion of the universe. These data led to the conclusion that the universe began from a single point and has been expanding from that point onward. At the time, it was hard for people and researchers to imagine a universe with a beginning and an end. The possibility of a universe that had always existed and was endless in reality was beyond people's imagination, and even today, researchers still face difficulties in understanding it. However, it is essential to consider these probabilities again. These new findings don't fit at all with what analysts have based for many years on the theory of how things came to be. Nevertheless, science has shown time and again that reassessment and receptiveness to novel ideas are an essential part of the scientific process, similar to the affirmation of certain hypotheses and observations. When Einstein was a child, it was accepted that the stars and planets were immovably fixed in the universe, and these specific designs involved a defined space. However, we now know that everything in the universe is moving. Planets orbit stars. Stars move within their galaxies at many kilometers per second, and entire galaxies move quickly through the universe, the destiny of which we can't yet even predict. This dynamic understanding of the universe challenges long-held beliefs and highlights the requirement for continuous inquiry and adaptation in scientific thought. Today, researchers are challenged to accept uncomfortable insights and to understand that theories are not absolute truths until they are thoroughly tested or confirmed by accurate observation. The possibility of the Big Bang emerged from the acknowledgement that galaxies are moving away from one another, and this distance is relative to their separation from Earth. This observation, known as Hubble's law, proposed that the universe was expanding. For quite a while, components such as cosmic background radiation and the redshift of light from far-off galaxies, as well as other cosmological designs, appear to support this theory. Anyway, it is essential to remember that previously, individuals who believed that the Earth was flat and that the Sun rotated around us also had physical proof for their assumptions until occurrences or technological improvements arose that provided a clearer and more precise picture. Right now, we are seeing a similar circumstance. Researchers predicted the new James Webb Space Telescope to affirm the assumptions connected with the Big Bang. However, instead, they have come across these 6 galaxies that seemed impossible. This advises us that science is continually developing and that researchers must be open to new discoveries and reevaluate existing theories based on the available evidence. The surprising discoveries challenge the current understanding and prompt a reassessment of well-established cosmological theories. Scientists use redshift as a tool to determine certain amounts in the study of the universe. Redshift, otherwise known as the Doppler effect, refers to the change in wavelength of light as the light sources, the spectator moves comparative with one another. To comprehend this, you can envision standing still and seeing a vehicle coming towards you. As the vehicle moves towards you, you hear the motor getting stronger. Anyway, once the vehicle passes you or gets away from you, the motor changes. This is because the sound of the motor changes as the vehicle moves. The same is true for light. When a light source, for example, a far-off star, moves towards us, the light we see shifts towards bluer tones. On the other hand, when the light source recedes from us, the light moves towards redder tints. This phenomenon is called redshift. Physicists have converted redshift values into speeds and distances for measurement in the study of the universe. However, it is important to note that small mistakes in these estimations could have massive impacts. The measurement procedures recently utilized are now under review, and it is interesting to see what results researchers will arrive at concerning the latest findings related to our universe. It is important to consider whether they are truly based on redshift mistakes or whether some researchers are just denying the facts. This is a question that requires thorough investigation and careful review of the data and methodologies used in the research. The current analysis and reassessment of measurement techniques highlight the evolving nature of scientific inquiry. Thank you for watching the video. As always, we remind you that you can post your questions in the comments box. If you liked the video, remember to hit the like button, share it so it reaches more people, and subscribe to the feed so you don't miss more content. Thank you for watching, and see you in the next one. This call to action encourages viewers to engage with the content, fostering a community of curious minds eager to explore and understand the latest scientific revelations. The investigation of our universe, with its vastness and complex celestial bodies, continues to dazzle and challenge researchers across the globe. From the early speculations of the universe to the latest discoveries made possible by cutting-edge technology, each revelation reshapes how we understand the universe and pushes the limits of human knowledge. One of the most significant and enduring questions in cosmology revolves around the origin and evolution of galaxies. Galaxies are vast cities of stars, gas, dust, and dark matter bound together by gravity. Grasping how galaxies structure and evolve is crucial not only for unraveling the mysteries of our universe, but also for confirming or testing existing theories, such as the Big Bang Theory. The Big Bang Theory, proposed almost 100 years ago, posits that the universe began from a particular infinitely dense point and has been expanding ever since. This idea arose from observations of the universe's expansion and the cosmic microwave background radiation, considered the remnants of the early universe's intense heat and light. However, recent discoveries, especially those made by the James Webb Space Telescope, JWST, have challenged some fundamental assumptions underlying the Big Bang Theory. The JWST, with its exceptional responsiveness and resolution, has identified worlds that defy conventional understanding. These worlds, dating back to within a few 100 million years of the Big Bang, are unexpectedly massive and luminous, suggesting a more powerful early universe than previously imagined. The implications of these discoveries are significant. They raise questions about the timeline and mechanisms of galaxy formation, driving researchers to re-evaluate existing models. For example, the discovery of galaxies that are already so developed shortly after the Big Bang challenges the notion that galaxy evolution was a slow and steady process occurring over billions of years. In addition, JWST observations have highlighted the complexity of cosmic evolution. It is now clear that galaxies can evolve rapidly and have significant star formation activities early in their histories. These insights compel astrophysicists to revise their hypotheses on how stars, gas, and dark matter interacted in the early universe to shape the first galaxies. Beyond reshaping our understanding of galaxies, these revelations underscore the crucial role of technological advancements in pushing the frontiers of astrophysical research. The JWST, with its infrared capabilities, allows researchers to look deeper into space and further back in time than ever before. By studying the light emitted by distant galaxies, astronomers can reconstruct their histories and unveil clues about the conditions that prevailed during the universe's infancy. The concept of redshift, a critical tool in cosmological research, plays a significant role in these investigations. Redshift refers to the phenomenon where light from distant celestial objects shifts toward longer wavelengths as they recede from us. This effect, known as cosmological redshift, provides valuable information about an object's distance and speed relative to Earth. Through meticulous analysis of redshift data, researchers can gather insights into the size, age, and evolutionary phase of galaxies observed by telescopes like the JWST. However, interpreting redshift measurements requires precise calibration and understanding of potential sources of error, such as gravitational lensing and instrumental limitations. In addition to focusing on individual galaxies, astronomers are also investigating larger cosmic structures like galaxy clusters and superclusters. These vast assemblies of galaxies are held together by gravity and offer insights into the distribution of matter on cosmic scales. By mapping the spatial arrangement of galaxies and measuring their velocities, scientists can trace the cosmic web, a tapestry of structure that spans the universe and defines the large-scale architecture of galaxies. The cosmic microwave background, CMB, radiation represents another invaluable source of information for cosmologists. Discovered accidentally in 1964, the CMB is the faint glow of radiation left over from the Big Bang itself. As the universe expanded and cooled, the extreme heat of the early universe diminished to a few degrees above absolute zero, leaving behind this ubiquitous background radiation. Detailed measurements of the CMB's temperature fluctuations provide a depiction of the universe's early stages, revealing primordial density variations that eventually led to the galaxies and cosmic structures observed today. Satellite missions like the Planck Observatory have mapped the CMB with remarkable accuracy, confirming key predictions of the Big Bang Theory, while also revealing anomalies that challenge current cosmological paradigms. One such anomaly is the presence of cold spots and unusually large voids in the CMB maps, suggesting surprising patterns in the early universe's density distribution. These irregularities have sparked debates among cosmologists, prompting alternative theories such as inflationary cosmology, an idea suggesting that the universe underwent a rapid expansion shortly after the Big Bang, a brief time of remarkable extension in its earliest minutes. The mission to comprehend the beginning of infinite structures stretches out past conventional astrophysical strategies. Molecule physical science especially analyzes lead at high-energy colliders, like the Large Hadron Collider, LHC, looks to duplicate the limit states of the early universe to test key particles and powers. Hypothetical structures like quantum gravity and string hypothesis offer theoretical roads for incorporating gravity with quantum mechanics, the two mainstays of current physical science. These aggressive hypotheses plan to bind together our comprehension of the universe at its most key levels, potentially accommodating the inconsistencies between Einstein's overall relativity and quantum field hypothesis. Additionally, the inquiry for dull matter and dim energy keeps on captivating cosmologists. Dim matter, theorized to comprise about 27% of the universe's complete mass energy content, applies gravitational impact on universes and other astronomical designs, regardless of emanating no perceivable electromagnetic radiation. Its tricky nature has prodded various observational and hypothetical endeavors to distinguish its constituent particles and grasp its job in cosmic dynamics. Comparably, dim energy, containing roughly 68% of the universe's energy thickness, drives the sped-up extension of the universe saw in late many years. Its starting point and properties stay baffling, presenting significant inquiries concerning a definitive destiny of the universe and the idea of major powers administering vast advancement. The quest for these major inquiries requires interdisciplinary cooperation, and the union of observational, hypothetical, and trial draws close. Stargazers, astrophysicists, cosmologists, and molecule physicists cooperate to unravel the vast code written in the light and construction of the universe. In end, our investigation of the universe is an excursion of discovery and reconsideration, a demonstration of human interest and resourcefulness. From the early trailblazers of stargazing to the present-day stargazers, looking from the perspectives of space telescopes, every age adds new sections to our enormous account. As we keep on disentangling the mysteries of universes, dull matter, and the inestimable microwave foundation, we inch nearer to appreciating our position in the immense span of existence.